Okay, let's unpack this. We often hear about artificial intelligence in terms of, these massive cloud data centers.
Right, rows and rows of hardware.
Exactly, humming away in some climate-controlled facility somewhere. But today, we're diving into a revolution that's happening in miniature.
Hmm.
It's agentic AI on the edge. This is where that intelligence, it leaves the cloud and it starts making these sophisticated, autonomous, real-time decisions directly inside the device itself.
And that device could be anything, right? An industrial robot, a smart camera.
Or even a tiny chip in your next pair of AR glasses.
And this isn't just a technical footnote. It really represents a foundational shift in how we build and deploy technology.
It sounds like it.
The scale of this transformation is immense, and it's happening right now. What we're trying to figure out today is how the marriage of agentic AI and edge AI is going to fundamentally change the market over the next 2 years.
That's our mission for this deep dive. We want to synthesize the 2025 and 2026 industry outlooks, the technical reports, and really understand precisely how this convergence is transforming core industries.
And not just how, but what's enabling it. The specialized hardware, the intent optimization techniques.
And crucially, the new security threats and, the evolving global governance challenges this new level of autonomy creates.
The context here is just it's non-negotiable because the growth numbers are staggering.
Okay.
We're talking about a global edge AI market that's, rapidly accelerating. Sources are showing it's expected to grow from what, $25.65 billion just this year, 2025?
Which is already a pretty significant market.
It is. But get this, it's anticipated to explode to $143.06 billion by 2034.
Wow. What's the growth rate on that?
That's a compound annual growth rate, a CAGR, of over 21%.
Over 21%. You just don't see numbers like that unless there's a fundamental market pivot happening, not just, some iterative improvement.
Absolutely. And the industry is moving even faster than the forecasts might suggest.
How so?
Well, we see that 29% of organizations are already adopting agentic AI,
Already.
meaning they're experimenting with or actually deploying these autonomous systems. And a further 44% are planning to deploy it within the next 12 months.
So if you add that up, that's almost 3/4 of the market.
Exactly. When nearly three-quarters of the market is either using or actively planning to use the technology, that signals a truly pivotal shift toward localized, self-sufficient decision-making.
So let's jump straight into part one then and define this new paradigm. The term agentic edge AI it's a mashup of two already complex concepts. Let's start with the base definition. What is the fundamental fusion happening here?
The simplest definition is this. It's the fusion of an agentic software architecture.
So goal-directed, highly autonomous systems.
Right. Fusing that with edge-class hardware. Low power, on-device processing. The core perception, reasoning, and actuation loop. It runs locally, right on the device itself. It doesn't need to check in with a remote server.
That sounds like giving every device, from a washing machine to a defense drone, its own focused, persistent intelligence. But what makes this AI system specifically agentic? It's more than just running a program on a local chip, right?
It is. The key difference is the software architecture, which centers around something called an orchestrator.
Okay, an orchestrator.
Think of the orchestrator as the device's chief executive officer. This CEO, it receives a high-level goal from the user. Maybe something broad like optimize my personal energy usage or identify potential machinery failures on line A.
So it's not waiting for specific step-by-step instructions.
Precisely. That orchestrator, which is often a compact, lightweight, or small language model in SLM, it breaks that high-level goal down into tasks. Then it delegates those tasks to a dynamic team of specialized agents.
So these agents are like individual specialists.
Exactly. They're self-contained AI units. You might have a computer vision agent, a predictive maintenance agent, an actuation control agent. The system autonomously chooses what specific tools to use next and how to proceed, all without constant human approval. It's adaptive workflow creation, not static programming.
And the edge aspect is the reason this whole architecture works in the physical world, bringing in that element of speed and reliability.
Correct. The edge aspect is the absolute necessity of running those time-critical functions: perception, rapid decision-making, and actuation directly on the device's onboard chips. We're talking about the specialized CPUs, GPUs, or NPUs.
Because the speed is everything.
It's crucial because it ensures millisecond-level, real-time response capability. If cloud connectivity is poor or contested or totally absent, the device keeps executing its mission. The cloud becomes an optional augmentation.
For heavy lifting, like big data analytics or training new models.
Exactly. It's not a single point of operational failure anymore.
That's the critical piece for you to grasp.
Hmm.
The driver here is speed and independence. You mentioned an autonomous car earlier. If the cloud is involved in the decision to brake, you're introducing a delay that could be catastrophic.
Mm-hmm.
That millisecond level capability is what's driving this massive industry investment. Let's break down the core benefits that explain this rapid adoption in more detail.
Latency is the prime mover, especially for safety-critical systems. Edge AI eliminates that round-trip delay inherent in the cloud.
And that delay can be surprisingly long.
It can. Consider a high-speed inspection system on a production line. It needs to detect a microscopic defect in a component that's moving at a meter per second. Or a surgical robot that needs immediate sensory feedback. That delay, that inherent latency of 100 or 200 milliseconds, it's just unacceptable.
So what does Edge AI deliver?
Edge AI delivers sub-10 millisecond decision loops, which is essential for anything that requires real-time physical control.
And beyond sheer speed, the biggest benefit that I think resonates with every sector is privacy and security, especially as we deal with increasingly sensitive data.
Edge AI fundamentally shifts the privacy paradigm. When sensitive data, like defense sensor, feeds in a tactical environment or patient medical imagery governed by strict requirements, like .pay.
Right, stuff you absolutely cannot have exposed.
Exactly. When it's processed and analyzed locally, its exposure to network vulnerabilities is drastically minimized. The data never has to transit wide-area networks or sit in potentially vulnerable third-party cloud storage.
So it's really the only way to meet compliance in some cases.
Often, yes. This localized processing is the only way organizations can meet those stringent regulatory requirements while still leveraging AI insights.
And when you keep the data local and run the processing locally, you inevitably cut the operational expenses associated with connectivity.
Absolutely. Think about the costs.
Yeah.
Processing data at the source dramatically reduces reliance on expensive, recurring cloud infrastructure costs.
You're avoiding all those ingress and egress fees.
All of them. And the sheer volume charges. Furthermore, it cuts down on bandwidth costs. For organizations deploying thousands or even millions of IoT nodes, say smart streetlights or environmental monitors, the savings on data transmission alone can completely change the financial model.
So it shifts from a high, unpredictable operational expense, OPEX.
To a lower, more predictable long-term capital expenditure, or CapEx.
And finally, reliability. If the autonomous system can't connect, it essentially turns into a paperweight.
That's the core operational advantage, especially in industrial or remote settings. Localized processing supports dependable, consistent performance regardless of external conditions.
So you're thinking of places like factory floors with a lot of interference.
A factory floor covered in radio frequency interference, a remote oil rig with satellite-only connectivity, or a battlefield where network connectivity is actively contested and degraded. Edge AI guarantees functional continuity.
Okay, that gives us the motivation, speed, privacy, cost, and reliability. Now let's look at how these systems are actually architected. You mentioned a multi-layered design. Walk us through the structure that distributes intelligence between the device and the cloud.
It's highly structured, usually built upon 5 layers to ensure an optimal distribution of tasks. We start, of course, with the interaction with the physical environment.
Which is the perception sensing layer, the device's fundamental connection to the world.
Exactly. This includes all the physical sensors, cameras, LiDAR, microphones, accelerometers, chemical sensors. Crucially, this layer also handles low-level firmware and initial signal processing.
So this isn't the AI making decisions yet.
Not yet. It's cleaning the data. Think analog to digital conversion, noise filtering, and normalization. It takes raw, messy data and prepares it before passing it up to the brain.
Any good examples of this in the real world?
A great example is Samsung's Bally Home robot. Its camera and LiDAR operate right here in this layer, constantly running low-level software for initial object identification and real-time obstacle detection.
And once that data is sanitized, it moves up to the edge cognition layer. This is the local decision maker.
This is the device's local brain, where the immediate intelligence resides. This layer is responsible for executing real-time, low-latency AI algorithms.
Like computer vision for object tracking?
Or path planning in a robotics context, or complex sensor fusion. Its sole purpose is to determine the agent's response in milliseconds, keeping that critical low-latency control loop running. If a factory robot sees a person unexpectedly enter its safety zone, This cognition layer instantly triggers the shutdown routine.
I noticed in the architecture outline, there are also layers for cloud cognition and learning adaptation, which handle the non-urgent heavy lifting.
Like model retraining and fleet-wide analysis, yeah.
But staying on the device, what is the layer that actually executes the decision?
That is the actuation layer. This is the physical output mechanism. The motors, solenoids, speakers, pumps, or control mechanisms the device uses to physically interact with its environment.
And this layer has to be incredibly robust.
Because this layer translates digital decisions into physical actions, it must be engineered for inherent redundancy and safety.
So redundancy means if one system fails, another takes over.
Yes. For a self-driving system, that means multiple independent braking circuits. For a high-speed robotic arm, it means physical limiters and software overrides to prevent unsafe speed or torque, regardless of the command sent from the cognition layer.
It's the physical failsafe.
It has to adhere to stringent functional safety standards like ISO 26262 for automotive applications because autonomous actions have life-critical implications.
Given those high stakes, especially in defense or complex industrial settings, the systems are rarely allowed to operate entirely unsupervised. This brings us to the mandatory inclusion of human decision points, human in the loop versus human on the loop.
Right.
These terms are critical, but they're often conflated.
They define the level of human control over an autonomous system's final action. Human in the loop is the most restrictive and the safest model.
So what does that look like in practice?
It means that while the AI agent might handle all the complex perception, tracking, and targeting, a critical, irreversible, action-like weapon discharge, the use of force, or a major system shutdown, requires explicit human authorization.
So the system literally stops and waits.
It stops and waits for a physical or digital go-ahead. The human is the final essential gatekeeper for every single critical decision.
And I imagine in some scenarios that's legally required, not just optional.
Generally, yes.
Yeah.
Wherever the consequences are irreversible and involve high risk to life or infrastructure, think autonomous defense platforms or large-scale, high-power grid switching. The legal, ethical, and operational check is mandatory to distribute accountability away from the purely autonomous system.
And then there is human on the loop, which implies a more passive but still empowered role for the human operator.
That allows the system to operate autonomously, making its own decisions in real time based on the goals provided by the orchestrator.
But the human can still step in.
Exactly.
Yeah.
The human operator retains veto power and continuous situational awareness. They are monitoring the system's health and behavior and can override potentially harmful or inefficient actions at any moment.
And that's more common in
Yeah.
industrial automation.
Commonly used in less immediately critical but still high-value applications like complex industrial automation. It allows for peak efficiency while maintaining that crucial supervisory control.
That distinction authorization versus veto power is essential for understanding accountability in these systems. And that transitions perfectly into part 2, where we discuss the technological engine powering all of this. None of this autonomy is possible without specialized, efficient hardware and software optimization. Let's talk about the hardware race, starting with the dedicated AI workhorse, the neural processing unit, or NPU.
The NPU is the engine of edge AI because it's dedicated to one thing.
Yeah.
Efficiently processing neural network calculations.
Right, it's not a general purpose chip.
Not at all. It achieves exponential performance gains over general-purpose CPUs or even traditional GPUs for these specific tasks. We're now seeing modern flagship systems on a chip, or sockets, delivering 45+ trillion operations per second.
45 TOPS. That sounds like a massive number. To put that in perspective for you, how does that compare to what was available just a few years ago?
I mean, 5 years ago, consumer chips were often measured in the single digits,
Right.
maybe 5 to 10 TOPS. Hitting 45+ means we have roughly a 10-fold increase in usable AI compute power in your pocket.
Wow.
This raw capability enables instantaneous features, running real-time, low-latency language translation on the device, or complex computational photography algorithms that blend dozens of images instantly to produce a single perfect shot. The power is what enables the agency.
And this capability is driving a fierce competitive landscape in 2025, especially in the smartphone space, where the chips are operating at incredibly tight tolerances like the 3-nanometer and 4-nanometer process nodes.
It is a critical battleground that forces engineers to make constant trade-offs between efficiency and raw power.
And you have different philosophies here, right?
You do. On one side, you have players like Apple, often prioritizing integration and power efficiency with chips like the A18 Pro. Its 60 TOPS neural engine is designed for seamless iOS integration and excellent sustained performance within the device's strict thermal envelope.
So they're playing the efficiency game
Uh-huh.
and then the alternative.
Then you have competitors like Qualcomm with the Snapdragon 8 Gen 4 featuring its custom Orion CPU architecture. Qualcomm tends to push the boundaries of raw power, especially for gaming and advanced features like ray tracing on mobile, alongside strong AI processing.
So there's this
A
tension.
constant tension. Apple often optimizes for the overall experience and efficiency, while competitors push for peak raw performance and advanced feature capability.
So the race isn't just about speed, it's about matching the chip's design philosophy to the device's thermal and power constraints. But the hardware race extends beyond consumer flagships, deep into industrial and embedded systems.
Oh yeah, where the demand for TOPS is even higher.
Right.
For specialized, complex, and high-performance embedded workloads, think highly articulated industrial robotics, autonomous delivery platforms, or sophisticated defense hardware, you need massive compute. That's where devices like the NVIDIA Jetson AGX Orin come in.
And that's a beast of a chip.
It's designed to deliver up to 275 TOPS of AI compute. It's built for environments that require massive parallel processing and can handle the associated power draw and heat, but still need to function autonomously at the edge.
And then, on the complete opposite end of the power spectrum, you have the chips that are truly enabling the future of advanced wearables and digital health by barely consuming any energy at all.
That's where companies like Ambiq shine with products like their Apollo 510 microcontroller unit. This chip exemplifies ultra-low power hardware.
How do they achieve that?
They utilize a proprietary method called subthreshold power optimized technology, or SPOT, which allows the chip to operate at voltages below the traditional threshold. This can deliver up to 90% energy savings compared to conventional chips performing similar tasks.
90% is incredible. For you listening, if you're wearing a fitness tracker or a continuous glucose monitor, what does a 90% energy saving mean in your daily life?
Well, it's the difference between charging your advanced wearable daily or having it run continuously for 6 months or even a year on a single, tiny coin cell battery.
Wow.
This efficiency is critical for continuous monitoring. If you need to track heart rhythm, sleep patterns, or motion for predictive health insights, the device must function reliably for extended periods without recharging. CQT technology makes that level of continuous embedded intelligence practical.
That massive contrast, the 275 TOPS industrial monster versus the 90% energy-saving health chip, really shows the breadth and specialization of the edge AI market. But all this power, even the efficient power, generates a persistent foundational engineering problem: heat.
Thermal management is arguably the single biggest engineering constraint holding back performance gains on the edge today.
It really is the bottleneck.
It is. Unlike giant cloud data centers, which have rows of cooling towers and massive HVAC systems, compact edge devices must operate within extremely strict thermal budgets.
And they often have to operate without fans, right? They are sealed units.
Precisely. When you increase the computational power, say pushing that 45 plus TOPS processor, it generates significant heat in a tiny space. Dealing with that heat dissipation in compact fanless enclosures without causing the device to throttle performance.
Or worse, prematurely degrade the components.
Right. It requires massive engineering compromise. Engineers must sacrifice potential peak performance to maintain a safe, sustainable operating temperature.
And this is where the efficiency-focused designs gain an edge.
This is where designs like Apple's often gain an advantage, as they can sustain high performance longer without hitting those thermal limits.
So the size, power consumption, and thermal envelope of the hardware are all fixed constraints. If you can't make the box bigger or the chip cooler, the AI models themselves must be radically optimized to fit and run effectively. That brings us to Part 2, Section B, the necessity of shrinking these large, deep learning models.
It's a purely practical necessity. Traditional large language models are often hundreds of billions of parameters. They require gigabytes of memory and enormous amounts of power to run. They're impractical for the edge. So, optimization techniques are employed to reduce model size, memory footprint, and computational complexity.
Without sacrificing too much accuracy, which is the key.
That's the key.
What's the most effective technique we're seeing used right now, especially in consumer edge devices?
Quantization, hands down. It's a method of reducing the numerical precision of the weights within the neural network.
So instead of a very precise number,
Instead of using 32-bit floating point numbers,
Yeah.
you might use 8-bit integers, or even 4-bit integers.
I need an analogy here. Is that essentially like reducing a high-resolution photograph down to a JPG? You lose a tiny bit of fidelity, but you gain huge speed and massive size reduction.
That is an excellent analogy. You lose minimal perceived quality. The accuracy loss is often under 2%, but the model size can shrink by a remarkable 75% to 80%.
That's huge.
This massive reduction in memory requirement and computational cost makes it ideal for resource-constrained devices, allowing sophisticated models to fit into the small memory caches of NPUs.
And we also have pruning and distillation, which work together to create an even more efficient package. Let's tackle pruning first.
Pruning is the equivalent of trimming the fat. Neural networks are often over-parameterized. They have redundant connections or nodes that don't contribute significantly to the model's output.
So you're just cutting out the dead weight.
You're identifying those dead or low-value connections and eliminating them, sometimes removing 30% to 50% of the parameters. The challenge, of course, is careful tuning to ensure you only remove the truly unnecessary parts and avoid degrading the accuracy.
And then knowledge distillation is the final step, where the smaller model maintains the high performance of a much larger one.
Yes. Distillation transfers the capabilities of a large, highly accurate teacher model, which might only run in the cloud, into a smaller, more efficient student model that's suitable for the edge.
So the student learns from the teacher.
The student learns to mimic the detailed decision-making process of the teacher, rather than simply mimicking his final answer. And studies consistently show that these optimized student models can achieve 90% to 95% of the teacher model's performance while being significantly faster and smaller.
The sources gave a great concrete example using the NVIDIA NeMo framework. Can you walk us through that specific demonstration?
It was a fascinating illustration of the process. They took a large model, the Metalama 3.18b, and showed how it could be shrunk down to a 4 billion parameter model.
Okay, so cutting it in half.
Right. And they used two types of pruning. Depth pruning, which simply involved removing the last 16 layers of the fine-tuned teacher model, making it shallower, and width pruning, which reduced the size of the hidden layers in intermediate dimensions, making it skinnier.
And then they applied distillation.
In both cases, they applied distillation afterward to transfer that nuanced knowledge back into the resulting 4B student model.
And the final payoff is always maximized when you combine these methods.
Absolutely. The maximum efficiency is gained when you layer the techniques. For example, applying quantization after you've pruned the network. This synergistic approach often yields models that are 4 to 5 times smaller and 2 to 3 times faster than the original.
Which makes them perfectly suited for instantaneous deployment on the edge, solving that hardware thermal problem through efficient software.
Exactly.
This optimization race is focused on classical silicon architecture, but what about the glimpses of the future? Part 2 wraps up with two very futuristic concepts that promise to break current power and speed barriers entirely: neuromorphic and quantum edge AI.
These represent the next great leaps. Neuromorphic computing is it's brain-inspired, unlike conventional chips, which separate the memory and the processor.
Which forces that energy-intensive data movement between the two.
Right. Neuromorphic systems fuse memory and processing, operating more like biological neurons.
So less moving parts, less energy spent.
Exactly. This integration offers truly significant energy efficiency gains. We have the example of the NeuRAM chip, which features an analog computing architecture that is twice as energy efficient as current state-of-the-art compute and memory chips.
Twice as efficient.
For a battery-dependent edge device, doubling the energy efficiency allows for significantly more complex cognitive tasks within the existing power budget.
Twice as efficient is a game changer. And what about quantum neural networks, or QNNs, at the edge? That sounds like the ultimate speed upgrade.
It is in its early research, but the potential is explosive. QNNs leverage quantum properties to process data and solve complex optimization problems far more efficiently than classical systems.
And what kind of tasks are we talking about?
Think of optimization-heavy AI tasks like training complex, deep reinforcement learning models for robotics, or rapidly processing complex sensor fusion data.
And the data supports this potential.
Yes. Early studies suggest that QNNs can deliver 2 to 3 times faster training speeds and a 50% to 70% reduction in computational costs for these specific optimization tasks.
How do you even make that work on an edge device?
Well, to make this viable, engineers are developing hybrid quantum classical computing architectures. The classical AI handles the bulk of the initial processing, while a quantum component is used specifically for refining and optimizing the results.
So you're bringing capabilities previously restricted to massive cloud systems right down to the industrial robot.
That's the goal.
Fascinating stuff. Now let's move to part three and ground this in reality. Where is agentic AI making the biggest impact right now? We'll start with the sector that sees the most immediate transformation: manufacturing and smart operations.
Manufacturing executives view this transformation as crucial for competitiveness. A 2025 Deloitte survey found that a staggering 80% of manufacturing executives plan to invest 20% or more of their capital budgets in smart manufacturing initiatives over the next few years.
Wow, 80% investing a fifth of their budget. That's a huge commitment. What specific roles are these agentic systems playing on the factory floor?
They are driving value everywhere, from planning to execution. One key agentic role is solving the looming challenge of a retiring workforce.
Capturing that institutional knowledge.
Exactly. Agents are being deployed to observe and synthesize the specialized workflows of experienced staff, using that data to autonomously generate shift handover reports, optimize work instructions, and simplify complex equipment repair processes for newer employees.
That institutional knowledge capture is vital, preventing a massive loss of expertise. But operationally, how does Edge AI fundamentally change the maintenance model?
It completely shifts factories from reactive to predictive. This is predictive manufacturing, or PDM. Edge AI embeds intelligence directly into the machinery,
Yeah.
inside the vibration sensors, the pressure gauges, the motor controllers.
So the machine is self-diagnosing.
These agents analyze operational anomalies and forecast potential failures in real time. Instead of fixing a problem when the machine breaks, costing hours of unscheduled downtime, the system preempts the challenge
It alerts maintenance staff.
to replace a bearing that will fail in 48 hours.
And this autonomy is driving an explosion in physical AI robots and collaborative robots, or cobots.
The adoption is accelerating rapidly. Sources predict that the use of physical AI, meaning robots with advanced autonomy, is expected to increase more than twofold by 2027.
And Edge AI is what makes them safe to work alongside humans.
It's the key enabler because it gives cobots that real-time decision-making, allowing them to operate safely and dynamically around humans.
Give us some concrete examples of that low-latency robotics in action.
Take vision-guided assembly. A cobot equipped with edge-powered computer vision can adjust its grip strength and trajectory mid-task to handle components that are slightly misaligned or irregularly shaped.
So it's adapting to an imperfect world.
Right. Similarly, automated guided vehicles, or AGVs, use on-device LiDAR and Edge AI for path planning and navigation. If a human or a pallet unexpectedly enters its path, the AGV can instantly reroute around the obstacle without waiting for a central control system.
Which significantly reduces collision-related downtime and boosts throughput.
Precisely.
Moving from the factory floor to the patient's bedside, let's look at healthcare and personalized medicine, where the need for real-time outcomes is literally a matter of life or death.
Healthcare is one of the most critical environments for Edge AI, especially since chronic conditions account for about 86% of U.S. healthcare costs.
Wow, 86%.
Yeah. AI agents are set to revolutionize medical imaging with autonomous diagnostics. They can analyze CT scans, MRIs, and X-rays right at the scanner, often reducing the diagnostic time by up to 50% by prioritizing urgent cases and flagging microscopic anomalies for physicians.
And the adoption rate for this is incredibly fast.
It is. Predictions suggest 90% of hospitals are expected to adopt AI agents by 2025, largely for tasks related to patient data management, diagnostics, and operational optimization.
Remote patient monitoring, or RPM, is another massive application, especially using those ultra-low power chips we discussed. This addresses the challenge of managing chronic care outside of expensive hospital settings.
RPM is essential for efficiency and patient comfort. Devices powered by chips like the Ambic Apollo 510 enable continuous, passive monitoring of vital signs, heart rhythm, motion, respiratory rate.
And crucially, they can do it without being intrusive.
Exactly. They can use technology like millimeter wave radar for highly accurate fall detection without intrusive video capture.
That addresses the major privacy concern. If you're being monitored in your home, you don't want a constant camera feed being analyzed or uploaded to the cloud.
Of course not. Edge processing keeps that sensitive data local, analyzes the vitals for anomalies, and only alerts the system when a critical event occurs, such as a fall or a significant shift in heart rhythm.
So it moves healthcare from reactive care
to truly predictive medicine.
Give us an example of how that predictive capability translates into saving lives.
Sepsis is a perfect example. It's a life-threatening response to infection where early intervention is critical. Machine learning models analyzing real-time sensor data, body temperature, heart rate variability, respiratory rate, can detect early indicators of sepsis up to 6 hours earlier than traditional monitoring methods.
6 hours! That's a huge window.
Those 6 hours are often the difference between successful intervention and a tragic outcome.
The final major consumer sector we are looking at is retail and customer experience, moving toward totally frictionless commerce. What is the ultimate real-world example of agentic edge AI in retail today?
Amazon Go's Just Walk Out, or JWO system, is the definitive example of edge AI at scale. It's a massive, localized processing engine.
It's not just a few smart cameras.
Not at all. It uses custom-edge hardware and highly optimized transformer-based models to fuse simultaneous data feeds from multi-view cameras, load cells under the shelves, and 3D mapping data.
And all of that complex fusion tracking which shopper took which item and instantly calculating the bill has to happen locally in real time.
It must be local.
Yeah.
The system generates real-time receipts by processing all that data on custom-edge hardware. It's what ensures the frictionless experience and reduces average checkout times by up to 30%.
Because if they relied on the cloud,
The latency would make the system unusable, and the bandwidth costs would be astronomical.
outside of the store, agentic AI is also transforming aftermarket services for industrial and commercial equipment, which sounds like a massive new revenue stream.
It is a profit center. Agentic aftermarket services, where AI agents monitor equipment health, schedule preventative maintenance, and order parts autonomously, are poised to become significant revenue streams for manufacturers.
How significant.
They often deliver margins 2 times higher than the original equipment sales alone,
Wow.
because they represent a continuous value-added service rather than a one-time product sale.
And back inside the physical retail space, how does Edge AI handle the promise of hyper-personalization without invading privacy?
By using localized sensors for behavior analysis, Edge AI analyzes in-store movement patterns, often via 3D LiDAR sensors, which only capture shape and distance, not identity.
Ah, so it's anonymized.
Right. It combines that movement data with purchase history and demographics locally. It can then instantly push a hyper-targeted mobile coupon to your phone while you are standing near the relevant product shelf.
That instant context-aware delivery.
Is highly effective. Studies show this level of personalization can increase conversion rates for online retailers by 35%.
Our final application area combines everything we've discussed: autonomous systems and humanoid robotics. You mentioned earlier that latency is the critical issue for human-robot interaction. Why?
It addresses the core criticism made by leading robotics experts, like Hiroshi Ishiguro. He criticized the half-second latency delay inherent in accessing cloud computing for decision-making.
And that delay is noticeable to us?
It is. That delay, even if minor, pushes the interaction into the uncanny valley, where the robot just feels slightly wrong or unresponsive. Edge AI eliminates that delay.
So Edge AI makes the robot feel responsive, enabling true embodied AI.
That's the goal. Embodied AI uses a smart hybrid approach. Cloud AI is used for massive, expensive tasks like large-scale training and knowledge accumulation.
But Edge AI handles the here and now.
Right. It handles real-time perception, low-latency decision-making, and immediate physical interaction with the environment. NVIDIA's Project GR00T is a leading example, focusing on accelerating this hybrid model to enhance the dexterity and real-time perception of general-purpose humanoid robots.
And central to these advanced robotics are the small language models, the SLMs we discussed at the start.
Absolutely. Optimized for on-device processing, SLMs enable robots to generate natural, conversational responses, understand complex, multi-step commands, and assist customers. For example, 1X Robotics EVE robot.
So the robot can talk and understand without phoning home to the cloud.
It fuses speech, vision, and motion data locally, allowing the robot to function autonomously and seamlessly in real-world settings like retail and healthcare without needing constant internet checks to generate conversational text.
We've spent a lot of time talking about the technological promise and the incredible benefits, but this deep dive wouldn't be complete without addressing the risks. When you distribute autonomy across millions of devices, you exponentially increase the potential attack surface. Let's dive into part 4, managing the risk.
The distributed, multi-layered nature of agentic edge AI is both its greatest functional strength and its greatest security liability. Attackers have targets across the entire stack: the specialized hardware, the compressed software models, the learning processes, and critically, the physical actuators.
Let's systematically look at the attack vectors specific to each layer, starting with the perception layer, the device's sensors. How do you attack the eyes and ears of an autonomous agent?
The most common methods are deception, or physical blinding. For visual systems, you have physical camera blinding. like a high-intensity laser attack that saturates the image sensors, creating a whiteout condition in the vision stack.
Okay, so just blinding the camera?
And for audio systems, attackers can use malicious ultrasonic tones frequencies above human hearing to silently trigger hidden voice commands or unintended actions within the agent's microphone array.
So an attacker could be standing next to an autonomous system, making no audible noise, but the system is following their silent commands.
Precisely. And there's also the threat of sensor data manipulation via compromised firmware. An attacker might tamper with the device's internal calibration data, causing the firmware to alter raw readings.
So the AI is seeing a world that isn't there.
Right, say, scaling down LiDAR depth values so that the decision-making layers reason over bogus data, making the environment appear empty when it's actually full of obstacles.
That's unnerving. Moving up, the edge cognition layer, the local AI brain, is clearly the most high-value target.
Attacking the local AI brain is usually done through corruption or direct control. The most serious threat is model poisoning attacks.
How does that work?
This occurs if an attacker compromises the over-the-air update channel, a classic supply chain attack, and swaps the on-device model parameters. This can fundamentally alter the agent's behavior,
For instance.
perhaps causing a security camera agent to ignore anyone wearing a specific color jacket, or causing a vehicle to ignore a specific type of traffic sign.
And we can't forget the famous adversarial machine learning inputs that don't involve a hacker breaking into the network, but rather fooling the AI externally.
Exactly. These are carefully crafted physical objects designed to cause misclassification. We see stickers placed in specific patterns on a stop sign or patterned clothing that fools vision models.
So a human sees it correctly.
The human eye sees a stop sign, but the AI vision model, due to its blind spots, incorrectly classifies it as a speed limit sign, leading to unsafe operational decisions. These threats exploit the very way the model was trained.
If the attacker successfully compromises the cognition layer, they can pivot immediately to the action actuation layer, which involves direct physical risk.
This is the most dangerous stage. You face threats like unauthorized remote commands or robot hijacking, where stolen credentials or protocol flaws are used to remotely steer or reposition the robot.
But the really scary part is malicious commands.
The most critical threat is malicious actuator commands that override safety settings. For instance, injecting trajectories that make a robotic arm exceed its safe speed or torque limits, resulting in a dangerous whip-like motion that risks human injury or catastrophic equipment damage.
It sounds like a sophisticated attacker needs to conduct a multi-stage attack, blind the senses, poison the brain, and then seize the controls. But the vulnerabilities also extend back into the cloud and learning layers.
This creates systemic, fleet-wide risks. If the update channel is hijacked, a major supply chain attack, a malicious model update can instantly insert a backdoor across thousands of devices fleet-wide.
And what about federated learning, where the devices learn together?
That's a huge vector. A set of rogue devices, perhaps 5% of the fleet, can upload intentionally manipulated data. This is called federated learning poisoning.
And that biases the whole model.
It biases the resulting global model toward unsafe or malicious outputs. For example, if a fleet of AGVs relies on federated learning to refine their pathfinding, it would only take a handful of compromised units to intentionally bias the entire factory's pathfinding system toward high-traffic routes or collision points.
So, given this staggering list of multi-layered threats, how do organizations possibly defend against it? What are the necessary mitigation and defense strategies?
Defense must be foundational and comprehensive, protecting hardware, networks, and the ML models themselves. At the hardware and firmware level, the foundation is ensuring integrity from the moment the device boots up.
You mean secure boot?
Organizations must implement secure boot and signed firmware.
What does signed firmware mean in this context?
It means that every software image, every update, is cryptographically signed by a trusted source. The device checks that digital signature before loading the software. This prevents malware injection or unauthorized model swaps.
And that verification relies on a trusted source within the chip itself.
Precisely. That trusted source is the hardware root of trust. They utilize a hardware root of trust and trusted platform modules, or TPMs, to securely store critical cryptographic keys and verify runtime integrity. This creates an untamperable digital vault for the device's core identity.
And for defending the actual sensor feeds against the blinding and spoofing we discussed?
You need sensor and network hardening. This means building in redundancy. You cross-check sensors fusing data from cameras, LiDAR, and radar, and if one sensor feed shows an outlier, the system flags it and relies on the consensus.
And physical hardening.
You also need physical hardening, optical filters to block high-intensity laser attacks, and ultrasonic noise detectors to filter out or flag hidden voice commands. Network-wise, a zero-trust network posture is mandatory.
Zero trust posture. That sounds very aggressive. What does that mean practically?
It means that no device, no user, and no link, even internal ones, is automatically trusted. Every access attempt, every data transfer must be cryptographically verified and authenticated.
So no free passes on the network.
None. This is enforced with end-to-end encryption for all control links, so if an attacker breaches one point in the network, they cannot freely pivot to hijack the rest of the fleet.
Finally, how do we make the AI models themselves more resilient against those sophisticated poisoning attacks?
That requires ML robustness techniques. First, you must train models with adversarial examples so they learn how to recognize and ignore malicious or deceptive inputs. Second, you use runtime sandboxing to containerize critical perception and planning modules.
So if one part gets compromised,
If an attacker exploits one module, they are confined to that sandbox and cannot pivot to kill the actuators or access sensitive data.
and what about that complex problem of stopping the rogue devices from uploading manipulated data during fleet-wide learning? How do you prevent federated learning poisoning?
That requires using what are called Byzantine resilient aggregation techniques. In federated learning, data is aggregated from many different devices.
And these techniques spot the liars.
Byzantine resilient systems are designed to detect and discard manipulated data uploaded by rogue devices, the Byzantine generals problem applied to AI. They analyze the statistical similarity of incoming data updates and reject those that deviate significantly from the consensus.
So it's a digital immune system for the fleet.
That's a great way to put it. It detects the one rogue device trying to lie to the group.
That is a staggering list of necessary defenses. This level of complexity is why compliance and governance are rapidly becoming mandatory, not optional. Let's finish our deep dive by looking at the rising tide of AI governance and compliance.
The legislative momentum is undeniable. Because the U.S. lacks a unified federal law, states are leading the charge. Already, 8 U.S. states have fully enacted AI legislation, and 18 states have both enacted and proposed new laws.
And what's the focus of those laws?
The vast majority of these focus on accountability, transparency, and data privacy related to autonomous systems.
But without a federal standard, how are large companies with nationwide operations standardizing their approach?
They are turning to robust frameworks like the National Institute of Standards and Technology, or NIST, AI Risk Management Framework, the AI RMF.
And what does that do?
It provides a comprehensive, voluntary guideline built on 4 core pillars: map, measure, manage, and govern. It helps organizations responsibly manage 7 key risks, including validity, reliability, safety, security, and crucially, fairness and bias management. It provides a common language for risk discussion.
The NIST framework gives us the map, but global governance is setting the legal bar that affects U.S. companies operating internationally. What international frameworks are the most influential right now?
Primarily 2 key sources. First, the EU AI Act. This is the most comprehensive legislation globally, establishing strict risk-based requirements.
So they categorize the risk level of the AI.
Exactly. High-risk applications like critical infrastructure, law enforcement, or medical devices face intense oversight, documentation, and pre-deployment testing. And like the GDPR before it, this act affects U.S. companies that offer products or services to EU residents, effectively making its standards global.
And the second major influence is a global management system standard that everyone is watching.
That would be the ISO/IEC 42001.2003 standard. This is a management system standard that guides organizations in developing responsible, transparent, and trustworthy AI systems.
Not legally binding, but influential.
It's not legally binding, but it acts as the global blueprint. It is heavily influencing how lawmakers worldwide are drafting and refining new AI legislation, creating a unified global playbook for ethical and accountable AI deployment.
Central to all of these frameworks, state laws, NIST, and global acts, is the concept of explainability. We have to know why the AI made a decision. Why is explainability especially challenging for edge AI?
It's challenging because of the inherent trade-off between speed and transparency. Organizations must be prepared to document and audit the decision-making process. For edge AI, the models are often highly compressed and operating in real time on resource-constrained hardware.
So you can't run a big, slow analysis program on it.
You simply cannot run computationally heavy, cloud-based explainability methods that would take seconds to process. The latency penalty would negate the benefit of using edge AI in the first place.
So the goal is lightweight transparency.
Exactly. Developers must rely on lightweight techniques, such as saliency maps, which visually highlight the parts of the input data the AI prioritized, or context-aware explanations that quickly log the decision parameters. They offer transparency without compromising that sub-millisecond performance,
And that capability is absolutely crucial for building public and regulatory trust.
especially in safety-critical sectors, like autonomous transportation and healthcare.
This has been a true deep dive. We've charted the dramatic market shift toward agentic edge AI, driven by the indispensable need for low latency and high privacy. We've seen how specialized hardware, the NPUs, the ultra-low power MCUs, the thermal constraints and optimization techniques like pruning and quantization are making this shift possible. We've explored the tangible benefits across manufacturing, healthcare, and robotics, and we've identified the acute, multi-layered security risks this autonomy introduces, demanding strict compliance with emerging global governance frameworks focused on accountability and explainability.
And this convergence sets the stage for the next decade. Think of the projection that by 2030, intelligent AR glasses are projected to be nearly as ubiquitous as smartphones, all powered by these tiny optimized AI chips. If the future workforce, supported by agentic AI that captures institutional knowledge and humanoid robots that adapt instantly, is indeed the future of our physical economy, then the limiting factor won't be processing power. It will be our ability to guarantee the trustworthiness and explainability of every millisecond-level autonomous decision. You must now consider, how will you audit the brain of a machine that never connects to the cloud and whose decisions happen too fast for a human to veto?